to be engaging, even if I'm a little tired here. So it's one of the things that's interesting is that when you look at the program of the workshop, and you look at every talk, and everybody is telling you, well, exoplanets, directly image, it's fantastic, we get the photometry, we get the spectrum, we can study the atmospheres and stuff. But when you look at the program, there's a talk about astrometry, which is this talk here, and that's not so much about the spectra. And there is a good reason for that, is that without the astrometry, there's very little you can do on these planets. And that's something we should not be taking for granted. And I'm hoping through my talk that I'm going to show you how we can deal with that, but why it's important also. So why is it important? Well, when you have an image with a blob next to a star, you first have to figure out whether or not it's aligned, it's co-moving with the star, it's physically associated. And so that's the kind of pictures you get here. So I think that's from Julien's paper here, where you have the relative separation of the companion with respect to the star, and its motion on sky, whether it's a background source here. So here you have the proper motion in this direction, and here these little wiggles are parallactic motion. And so in this case, you can see that the data, I think it's in red, is kind of following the predicted position. And then here in this case, the data is really not following the predicted position if it was a background source, and it's actually a physically associated companion. And that's why you need two or three epochs, 2 or 3 images before you can claim that you've discovered something. You first have to check that it's not a background star. So that's really nice. But there's a cautionary tale with that. It's in here. It's in your error bars here. And you look at this figure from Dimitri Maury's paper on IM loop. So this was his astrometry, I think, on his VLT data in 2008. And this was his astrometry that he got from a very, very old Hubble image. And the error bars are ginormous, but it looked like at first sight that it was consistent with a physically associated object. Dimitri, being very careful, he went back to it. And in the end, it turned out that both this error bar was, at this point, it was actually way too big to say anything, because you see these two are overlapping, so you cannot rule out the probability that it's a background star. But you go back to it, you get astrometry with small error bars, and you find it's a background star. Hidden in this, on top of it, is something that you should be careful of. The Hipparcos parallax and proper motions were wrong. So they had to redo it on top of it. But that's a cautionary tale, and a lot of this hinges on the size of these error bars. And I'm going to try to explain to you how to get these points right and to get the error bars a little bit under control. Okay, why is it important? We have these beautiful pictures of directly image planet, but we don't measure the mass. We don't directly measure the mass. All we're measuring is the luminosity and the spectrum of the planet. And the only way to get the mass is through some argument associated with orbital motion. So it could be combining orbital motion with direct images here. So this is a paper from Justin Krepp, with radial velocity trends. You combine those two, and if you start having a little bit of curvature within your RV trend and within your direct images, you can really nail down the 3D orbit of your companion and its dynamical mass here. So for this object, Justin found dynamical mass around 68 Jupiter masses. But you could do the same argument, something a lot less massive. That's a planet. So that's one very nice thing that you can do with orbits. And once again, it's all about getting your error bars right here. You can look at a planet in a disk. For Beta Pictoris, there still hasn't been really a dynamical mass like estimate based on the interaction of the planet and the disk, because this is actually really, really hard to do. I think there's going to be a talk later today that's going to talk about this a little bit. But once again, the astrometric information is really, really important. And the other technique that you can use is to use these multiple systems. And I think Travis talked about this during his talk a couple of days ago, where you can, based on the orbital motion that you get for the 3 planets in this system here, or actually there's a 4th one in there, you can start putting bounds on the dynamical mass of each planet, so the system is still stable after 20 or 30 or 50 mega years, or whatever is the age of the system. But once again, the astrometry measurement is the fundamental measurement underlying all these estimates. So why is it hard? Is there a little cartoon? So assume that you have a planet here in your detector, and you have speckles that are 20 times brighter than that. So of course you don't see it in your reduced image. And you're running your reduction, whatever algorithm I talked about 2 days ago. And you're just trying to get the centroid of this blob here. Of course, you don't have a blob. You have something that's pixelated. And assume that your algorithm does something pathological. That is, it just, it kind of like makes these pixels a lot fainter and these ones a little brighter, but you still have a good detection here. Well, when you just try to estimate your astrometry, you're done with something like this and you get it wrong. And that's why you have to be a little careful when you do data reduction in order to get this position measurement. But before we get there, we have to think first about the instrument calibrations. So this is very basic. Some of you have gone and jumped through these hoops for a while now. Some of you may be new to the field and might need a little reminder of what is going on. So I'm going to spend like about 5 or 10 minutes on this. But pretty much a story here. You want to know how the sky maps on your detector. Your detector is a uniform grid of pixels. The sky is whatever it is, and you have a bunch of optics in between, and you want to know how one maps into the other. So the first thing you have to do is to correct for distortion. So this is an image, I think, a figure from a paper with Keck. One of the common practices to do that is to actually look at the crowded field on your detector. And the crowded field actually has a counterpart with a very well-calibrated instrument, which in this case is Hubble. I think the little circles are where it's expected to be with Hubble, and then you have the points in there, that's where you're measuring it. And then you apply some distortion correction. So this is the difference between where it is on the Hubble image and where it is on the Keck image. And these vectors here correspond to the difference between the two positions. You fit a lower order polynomial to this distortion map, and you get residuals that look like this when you compare the two images once again after you've fitted for your distortion through a lower order polynomial. And so then you have a really good map of how the sky projects on your detector. And this is what happens. These are the residuals. Once this is before you apply distortion correction, this is after you apply distortion correction. And Quinn actually has a really nice paper on how to do that with GPy in the former SPA proceedings. So that's the distortion. Then you need to figure out what is the size of a pixel on the sky, and where is north on your image. And the way we do that, we look at binary stars. So you put a well-known binary star in a detector. So either it's a binary star with a well-constrained orbit. So you go to the Washington Double Star Catalog, and you have these very nice binaries with grade 1, 2, 3, 4. So you pick one with grade 1, hopefully. Grade 2 if you're unlucky. Yeah, it's hard to get a grade 1. And so then you measure the relative distance and angle of the two components of the binary star. And based on the predictions of the model that you have on your catalog, you know exactly what it should be at that epoch. And so this way you calibrate your instrument and you measure your place. So the place scale would be the distance between those two, and the PA offset would be it should be, for instance, north would be here in this direction. And then you can start playing this game where you're moving your binary stars all over your detector as much as you can, and that's kind of a sanity check that your distortion correction was right. If you start finding things that are discrepant or not consistent, then you should start scratching your head and go back to your calibrations. The other option is to look at some binary or some, this is like the theory A or B, I don't remember, some system that has simultaneous epoch with a well-calibrated instrument. So you've observed it 2 days before with Keck, you trust Keck very much, you observe it with your favorite instrument, and you know where it was in the Keck images because you trust Keck, and you use that separation to actually derive your place scale and your PA offset. And this is the case of theta or here. This is a comparison between the GPy image where it's north is not up, and this is the Mageo image where north is at this time. And you compare these two images and you align it. Actually, I don't think we used this for GPy, but we did the similar trick with a different source. Mm-hmm. It was part of the measurement? Okay, yeah. Okay, so that was all about the calibrations. That was quick, but I hope if you knew about it, great. And that was just a reminder. If you didn't know about it, you can go back to the slides and look at them a little more carefully. So now the question is how to do the astrometric estimates when I said your planets are a lot fainter than your speckles. So this is P1640 data, and I mean, this is with an AFU. It's a movie I'd like to show you. Probably some of you have already seen it here. So you see your speckles are moving with wavelength here. Okay. So can anybody see the planets? Because they're there. So HRD 79b is here. Doesn't move. Yeah. And C is here. It doesn't move. Sorry? This is H-band. And D, there is no way to, it's somewhere here. It's somewhere in these blobs, but you don't see it in the raw image. So that just gives you an idea of how, you use one of the algorithms that I showed you on Friday, and you'll get these nice images where you see your planets and they're beautiful. But it's hard to actually get a meaningful measurement of the flux, but also of the astrometry, because you're just polluted by all these speckles that are just getting subtracted and so on. And that movie was here to show you, to give you a little bit of a flavor of how hard this is. So, first step, we have to align our images. The image alignment is really, really important for the data reduction. If your images aren't aligned, that is, if your speckle don't fall one on top of the other, then any low-key or PCA algorithm, I'm saying don't fall on top of each other in the reference library, then your reduction algorithm is just not going to work really well, because you're going to be trying to calculate correlations on things that are just not correlated because they're not aligned. But more than that, the alignment is important also for the astrometry. If you're going to do a precise measurement of the relative position of the star and the companion, you should have in all your images the star being on the same tenth of fifth of a pixel and your companion on the same tenth of fifth of a pixel. And in some cases, you're going to be able to align them sort of well, so you can have a nice detection map, but your alignment is not going to be precise enough to do the astrometric measurement. So all I'm going to talk about here is how to do this with integral field spectrographs, because these are the new nice sexy instruments. But most of these considerations here apply to any type of instruments. I'm just pretty much trying with the hardest. And at some point during the talk, I'll just say, well, look, you can apply this technique for other type of instruments. So when you have nice satellite spots, so what are satellite spots? Assume you're putting in the pupil of your coronagraph this regular grid here. Or the other way you could do it, you could put on your difframal mirror some modulation pattern that's going to behave as a diffraction grating that creates this nice little round spots here around your star. Okay. So you can fit, you know what the PSF of those should be. I mean, hopefully you know that. And you can fit the location of these 4 points here. And based on the location of these 4 points, you can find that the star is at the intersection of the 4 points here. All right. And not only that, but by measuring their separation, you can get an empirical measurement of this scaling glow here that should go as 1 over lambda, but does not always go as 1 over the wavelengths. You might have some errors in your wavelength solution or some dispersion that you don't want in your instrument. So that's what I'm saying here. Find the location of each spot, fit each spot to a model, derive the scaling law and the location of the star in each slice, and then you shift and rescale all images, and you're ready for your PSF abstraction. And here everything has been well aligned, so you're going to be able to do your astrometry precisely. Here you can start seeing a problem here. This is a broadband GPI image where we don't put the. This is actually done in a polarimetry mode, where you do not have this nice speckle motion because you're just integrating over the entire H-band filter. And here you don't have these little spots to fit. So that's going to be a problem here. And I'll show you a little later how to deal with that. So now you have crummy satellite spots. So this is P1640 data. And now you can see that my satellite spots are not completely round. And they have these like 4 dots around them. 1, 2, 3, 4. We don't have a good model for that. So the 4 little dots here, it's just low order wavefront errors in the instrument that are hard to remove. And they're associated with the optical setup at Palomar. The elongation here, I mean, they're not like really, even the core is not really nice and round. That is something more fundamental, is due to the fact that the spectral resolution of P1640 is, I think, 2 to 3 times smaller than the one of GPI. So this is actually a 2 or 3% band image. And so you have some elongation just due to the chromaticity. The GPI images look very, very monochromatic, so they're nice and round. And trying to fit a model to that can become really, really hard really quickly. I've tried a few times, and I just never really got to get it working really well. On top of it, you could have images like this, where, okay, the movie doesn't play, it doesn't really matter, where for some reason the spots are just not there. Because somebody didn't put the grid, because we forgot to put the modulation on the difframal mirror to make these spots appear based on the difframal mirror. Now, you'll ask me, well, I don't really care. I'm just going to get data with a better instrument. Well, that might be true if you have a very, very generous stack. But for the astrometry, actually, and for the orbital motion, that is not the point. All these points are really precious. Even if you're not going to get your good spectrum in your precise photometry, these planets have very long periods. So every data point is important. I mean, in the example I showed before for the Hubble images of HRE 79, that data was taken in 1998. And that data was nowhere close to the quality of these images. But if you can retrieve their locations in these images, in this archival data, you're going to be able to do great science with those. And so you also have to have reduction algorithms that don't work on good data. I mean, maybe 50% of the time you'll have your perfect data set and the previous method is going to work. The rest of the time you're going to have to deal with whatever is sitting on the archive or whatever happened that night, and you don't want to wait another year to for instance, to confirm your companion. So if you cannot fit the spots, then you can do the alignment relatively. So in that case, you pick a slice, and first you have to, you pick an image in, so do I have it here? No, I don't have it here, sorry. So you pick an image that's your reference image, and you're going to align everything to that reference image in your entire observing sequence. So the first step is to retrieve the scaling law between the different wavelengths. And to do that, you do it in the UV plane. So you take the Fourier transform of your 2 images. You cross-correlate the energy in each Fourier transform, their modulus. And because the information about the XY position in your UV plane is all in the phase, if you just cross-correlate their modulus, you're going to be able to derive the scaling independently of whether or not the images are aligned. Once you have the scaling law, you stretch, squash every image, and then you align them relatively using some subpixel image registration algorithm, and that's the one I'm using. I mean, if you guys, this is really efficient. This runs really quickly. I mean, I have the reference over there, but If you guys want to use it, this is a really, really neat algorithm. And so now you've aligned everything. All right. So you're ready to do your PSS subtraction, and the star and the planet really land on the same pixels. But you still have no idea where the star is. In the previous technique, you knew where the star was. Here, you have no idea where the star is. And I'll go back to that in a few minutes. All right, so here's the results of this image registration process. So here you have an observing sequence. This is a cube of 37 wavelength. And so these are like, I don't know, I have 15 cubes in this observing sequence. And all I'm looking at are the X and Y shifts as a result of this image alignment here. And you can see that it really behaves very nicely. I mean, not so nicely, but this motion here is simply the star that's moving the detector as a result of atmospheric differential refraction. And when we were discussing that actually a few days ago with Marshall, he gave me this really neat explanation of think of the atmosphere as a prism, and it's just going to disperse and move the star a little bit on your detector. You can turn on the atmospheric differential correction, and now you're down to the same pattern here. You have some residual, but you are going from plus minus 1 pixel here of dispersion to plus minus 0.2 pixels here. So putting your atmospheric differential corrector has really, really improved this stellar motion here. You should still try to realign even better than that. But of course, you're starting with something that has a lot less noise. So hopefully, you're going to be doing better on your alignment, but also on your astrometric precision. And that's something to watch for when you're looking at this IFU data, whether or not the... You have a question?
Yeah. Why is there like a sinusoidal variation in the position?
Okay. On this one?
No, in the top.
Oh, this?
No. There's like a more...
That's called somebody screwing around with the GPIAO because that's commissioning data. I don't know what they were doing. I mean, they were just changing gains in the loops and stuff like this. So that's commissioning data. So usually it should just be straight up. So once you've done that, you're ready. You have your images that are well aligned. So you have your speckles that go vertically in these cubes. And then you have your companion that goes diagonally. And you do that trick that I explained on on Tuesday. You pick an image here that's going to be your image you want to analyze. You throw away the images that are a little too close, for which you might have some signal crosstalk here in between the companions. And you take all the other ones and you put them in a big PSF library, and then you run your favorite least squares algorithm. And you get something like this. This is the Palomar data on HRD79. So then, if you want to get the astrometry and the photometry, as I said on Tuesday, there are plenty of different ways to do it, injecting fake planets and so on. I am not going to have time to go over all of those. So over the next 10 minutes, I'm going to tell you what I'm using. Doesn't mean it's the best way to do it. It's just that's what I'm using here. And here that's as good as I can do it. Otherwise, I would need a 2-hour talk to go over every way you could go about it. Actually, I had a few questions regarding the comparison of different algorithms after my talk on Tuesday. And one point I would like to make is I pretty much made the statement that all algorithms were equivalent, provided that you spent enough time tweaking them. There's also provided that, you need to be happy with your false positive and your false negative probabilities. And pretty much all the comments the feedback I had after my talk is like, well, what if I'm not computing my false positive and my false negative probabilities properly? And that's true. If you don't do that properly, or if you include the calculations of your false positive probabilities within your algorithm, and you don't do that right, then it's not working. And if you actually want to Dimitri Mawe had a really nice paper on the archive a week ago explaining how to go through these calculations. And I really encourage you to go through it. I mean, this is not a topic that's not covered in the workshop, but I really, really encourage you to read it to understand the formalism behind that. Okay, so this is what I went through during the hands-on session. And this is just associated with PCA. So this is what you have in math after you've reduced your data. So if you remember the notations, you have this is a random realization on your image of your instrument response, and you're projecting it on this PCA basis. And this PCA basis has been derived based on all the reference image in your reference library. So that's when you have no signal. When you have astronomical signal, then you're projecting also the astronomical signal on this PCA basis here. And what we want to find is what this looks like on SCI. We don't really care what it looks like in the reduced image. What we want to find is what it really looks on SCI. And what we can do, we can just take this reduced image that I called F here, and fit in the least square sense a model of our astrophysical source that has been projected through the PCA basis. So this is kind of the basic equation that we're trying to solve for. Just want to take a time out and does it make sense? You're just taking the model of your source that's been projected through, this is what the algorithm does to your source, and you're just fitting it to your reduced image. And you're doing the least square sense because, once again, least square estimators are nice. So then you just go through it, and you find a semi-analytical expression for the astrometry and the photometry. And all of these numbers, this is just a bunch of correlations. So N0 is the location of my objects, of my point source. And beta, it's its flux. And all of this is really nice because anything that's correlations, Fourier transform do it very quickly for you, so you don't spend too much time injecting something and then rerunning your reduction. You can do it pretty quickly. And that's what was running in the hands-on session when I was running this little demo about the Fourier modeling for point sources. And when you do that and you inject a fake point source in your data, and then you apply this formula and you try to retrieve its photometry, so that's the SNR of the fake point source I injected, so something at SNR 3, something at SNR 15. You don't do the Fourier modeling, you see these curves here, where the flux is being eaten up by the algorithm. And you run your Fourier modeling, and then you see these flat curves here. And here I know what I've injected, so it's exactly what I have injected here. At lower statistical significance, you have a little bit of wiggles here. That's going to be your uncertainty. That's going to be your error bar. There's only so much you can do with this. When the SNR is higher, this is really flat. There's no wiggles, and you can just really nail down your error bar. And for the astrometry, it's the same story. This is I think this is the difference in pixels, in arcseconds for P1640, between the location where I injected it and where it's being measured for different modes. Now, if you go back here, this is a least square estimator. So that only works if the noise in your residual image is Gaussian zero mean. So if it's not Gaussian zero mean, you're host. And the way to deal with that is to just try different size of zones until you find a very nice reduction with your residual being Gaussian zero mean. The other reason why it's not going to work is that you need to have no signal from the companion in the reference library. If you have some A here hidden in these PCA bases because you've done ADI and you have some of the astrophysical signal, this is just going to break down. So there are different ways to deal with it, but the really simple, low-tech way to deal with it is just to make sure you have no signal in your PSF library. And so this is an example of IFS data where your speckles don't move here, your companion moves. And you're creating a zone here. So this is an azimuthal zone. And you're putting the companion right next to the edge of your zone. And you're only choosing images in the PSF libraries at shorter wavelength here. And this way around, you're making sure that the companion is never in your zone here. Oh, no, sorry. You're shooting those ones, and the companion is never in your zone. And by playing this trick, you can just make sure you're creating a companion-free PSF library. And then you just, for each slice which you're at, or for each image, for each cube that you are within your ADI sequence, you're just putting, I mean, when you have ADS or SDI, you need to put them in the corners, so you have 4 different configurations. And for each image, you're choosing the configurations for which you have the more references. So depending where you are in your observing sequence or where you are in your wavelength, you're going to choose a different geometry and a different set of reference images. And that just kind of, this is cheating, this is a way to cheat the system, but that kind of works out. Now, I'm going to show you an example where it worked out. Clearly, by doing that, you're going to sacrifice in SNR because you're willing to live with a smaller PSF library. And there might be cases where you just can't sacrifice in SNR and you have to find something else. And that's something that I haven't gotten into it yet, and that's something, if you guys want to think about it, how to do it, I really encourage you to do it. So this is the results you get. So this is the P1640 data on HRE79 B and C. So here are the spectra that you're getting. These different lines here are doing the same reductions for, using this approach for different zone geometries and different number of principal components in my expansion. So you can see that the zone geometry sort of impacts it because, I mean, there is a little bit of a scatter here. And that's just to the fact that you don't really respect all the reduced speckles are exactly perfectly Gaussian. I mean, they're not. So your least square estimator is going to give you some kind of not a perfect answer. And this is the astrometry. So this is the location in pixels here as a function of wavelength. And we're actually using this information as a function of wavelength as part of our Force-Alan probability. This is what a speckle would look like as a function of wavelength. So we have something really flat. So we're pretty confident that we've actually detected a point source. And then something I forgot to put in this slide. You can just, it's not very rigorous, but you can derive your error bar based on the entire scatter of all of these values. And you can come talk to me offline of how you actually really do it very rigorously for the error bar. I just haven't had the time to put it on this slide. This is for HRE79D. Now this is starting to be lower SNR, so there is a little bit of junk here, but still, this is not following the trace of the speckle. And for HRE79E, this is starting to be a very, very low marginal detection. But as far as astrometry goes, this is pretty flat. This is actually not flat. This is a little scary. What we've done for E, we've actually done the same analysis on a bunch of locations at the separation of the planet, and they all follow these lines perfectly. So they actually follow what a speckle should be looking like. This is the only one that doesn't follow these lines. So, and that happens to be the one where you would think where HRE79 is. So we've assigned a low Force-Alan probability to this detection. Okay. So now you have the location of your planets in pixels in your detector. And if you've done the alignment with very nice satellite spots, you're done. You know where your star is. And you know, you know where your planet is. So you have the relative distance between star and planet, and you can move on to the next step. Now, when you're in these pathological cases, they're actually not that pathological. They happen very, very often. Then you need to figure out where your star is. And this is how I'm going about it. So this is a broadband image. So now you can see that these satellite spots are elongated in the radial direction. And you can assume on these images that your atmospheric differential refraction has been well corrected either thanks to relative alignment when you have an IFU, or when you just have a broadband image. In that case, you have to assume that your ADC is doing whatever it's doing and it's working well. Of course, if your ADC is not working and you have a broadband image and you have a motion through bandwidth of like 1 or 2 pixels, these are not going to point towards the star. And I'm not talking about this pathological case. I'm talking about a case where things are well behaved and the spots are actually pointing toward the star. Then in this case, you can play this trick and you can use the Radon transform of the image. So this is something you're going to take home for reference, but the idea here is when you have an image with a line, the Radon transform of this line is just the projection along this direction. So this is this red line here. And then you're just turning this blue line here. And you see when it's orthogonal to it, then the projection is only on one point that's very bright. And so this is what it looks like. And this is something that's actually used to read barcodes, to read lines and figure out where lines are and how thick they are. And when you use that trick, you can actually find the location of the star. This figure might be a little cryptic, but if you stare at it long enough and you don't have time here, you'll get it. This was actually put together by Remy Soumer. I actually tried this technique just kind of randomly on a computer, and I was very happy that it worked. And then I told Remy, and 2 hours later, he was really excited because he saw the explanation as why it worked. So you take the Radon transform of the image. If you've really guessed your center really well, then you're going to have all your peaks that are aligned in the middle of your Radon transform. If you haven't guessed the position of your star really well, then the peaks of your Radon transform are going to do these little wiggles here. So you just integrating over the s equal naught axis, so the distance equals 0 axis of your Radon transform, and that gives you a very, very nice cost function that gives you a location of your star. And of course, you can apply that to these data where you actually do not have, I have the wrong figure. All right, forget about it. So you can apply it to the data where you actually don't have these spots, and you're only using the elongation of the speckles. And now what you're having is a contour here that's a lot fatter. So you have a bigger uncertainty on the location of your star, but it still works. And then once you have done all of that, you get the spectra from what I showed before, and you can put them out. But the point I was trying to make is that with this method, we've estimated the spectra, and we've done a joint estimation of the spectra and of the astrometry. And we've used the astrometry, actually, in the case of E, to convince ourselves that there was actually a detection. So I think that this problem should be done jointly. I mean, that's my take on this.